Okay, let's have a look at the problems in section 4.2. In 4.2 number 10 is you would to verify that A, B, C, D, that the inverse of this is 1 over AD minus BC times you swap the first main diagonal, and then you subtract the off diagonal. The main point to here is to show that both A times A inverse and A inverse times A was the identity. A lot of people only did one way. That was all pretty straightforward. In question 14, was to verify that 3, 0 was an eigenvector. And you do that just by computation. And we see that it is a 2 eigenvector because it doubles. And then in number 16, we had the system where we set x1 to be x, x2 to be x prime, and the system was x1 prime equals x2, and x2 prime equals minus 27x1 minus 12x2, and writing that as a matrix then is just x prime equals 0, 1 minus 27 minus 12 times x. And the only thing that people got mixed up with is they mixed up the minus 12 and the minus 27. Okay. Okay, so for the problems for section 4.3, we were looking at the matrix 1, minus 4, 4, and minus 7. We needed to find some eigenvalues, so we subtract r from the main diagonal, and we want to set equal to 0, then the determinant of this, which is 1 minus r times minus 7 minus r, which turns out to be r squared plus 6r plus 9. And so we see that minus 3 is only eigenvalue. And so then we're just trying to check 4 minus 4, 4 minus 4 times u1, u2. We want that to be 0. And we see that that happens when u1 equals u2. So the eigenpair, it's only one eigenpair. And so you had something like this. In number 6, we had the matrix 2, minus 2, 8, and minus 1. And so its characteristic polynomial is r squared. The trace is 0, so there's no r term. And the determinant is 4. So it's r equals plus or minus 2i. So again, we subtract 2i. So it's a pain that we have to deal with complex numbers, but it's also kind of easy because you only have to find one eigenvector. The other one is its complex conjugate. And so we see 2 minus 2i times u1 plus 8 times u2 is 0. The other one is a multiple of this, and so examples could be, if you set for the 2i, you could have u1 being 1, and then u2 is 2i minus 2 divided by 8, which is I minus 1 divided by 4. Or if you set u2 equal to 1, then u1 is minus 8 divided by 2 minus 2i, which is minus 2 minus 2i after you rationalize it. And so the complex for the other eigenpair, you have minus 2i, and then the eigenvalue is either 1 minus I minus 1 divided by 4, or minus 2 plus 2i, 1. Okay. This one kind of looks scary, which because it was a 3 by 3 matrix, but it actually kind of wasn't that bad. Because we see what the eigenvalues are going to be. We're going to have a 2, right? When we do figure out the determinant, we're going to get 2 times the determinant of this small 2 by 2 matrix, and its eigenvalues are 2 and minus 1. So you can see that the eigenvalues are minus 1, 2, and 2. 2 having multiplicity 2, and how many linearly independent eigenvectors it has. Well, you should subtract 2 times I time from the matrix, and you get and so you see then that when you figure out the eigenvectors, right, you're going to get 0 u1 plus u3, u1 plus u3. You can see that it's a two linearly independent eigenvectors. One is 0, 1, 0, because u2 could be anything, and the other one is u1 and u3 being opposite signs. So minus 1, 0, 1. Okay.